So our next speaker is Michael from Julia Hub. He will be talking about JSML, which is JuliaSim Modeling Toolkit.
Modeling language.
Language, sorry. Yeah, so let's welcome Michael. Okay, so good luck.
All right. Alrighty. You guys can hear me? Ooh, it's kind of loud, actually. Okay. All right, so I will just get started. Thanks, everyone, for attending. So I'll be talking about JuliaSim Modeling Language, and I'll explain what that is in just a second. But I want to start by talking about what ModelingToolkit is, because it really doesn't make any sense to talk about JuliaSim Modeling Language without really understanding what ModelingToolkit is. I want to make sure everybody's sort of on the same page there. So Chris Rackakis gave a nice talk yesterday. I don't know how many people saw that, but it was a workshop, actually, and talked about these things. So I'm kind of continuing on from there, but I wanted to give a quick summary. So ModelingToolkit uses a set of Julia macros to build models. And so I've just shown some examples of these macros up here. In ModelingToolkit, you need this concept of a connector. So you can see that you define a connector using the @connector macro. You have this concept of a model, so you use the @MTK model to define that. There's a bunch of other macros that are used inside the macros for things like extending, which is like inheritance, defining parameters, defining equations. And then ultimately, when you compose a system-level model, you use the @components macro to bring in those components. I think it's pretty intuitive to read, especially if you have a background in these sorts of things, I guess. But basically, the idea here is that this is a RC model. You create a resistor, a capacitor, a source, a ground, which are electrical components, and then you connect them all together over here. So that's how it's done in MTK normally. That's the normal MTK syntax. So there's a couple of complications that I want to talk about here that complicated. These complications arose really in the development of JuliaSim, which is the Julia Hub product. So these aren't really complications with respect to MTK itself, but really in our efforts to bring or to surface modeling toolkit capabilities in our product and in our graphical user interface. So the first thing that actually Chris alluded to even in his workshop was the fact that there's this uneasy tension between the imperative semantics of Julia and the sort of declarative intent of these macros. So one thing to keep in mind is that ultimately ModelingToolkit is going to do a bunch of symbolic manipulation, essentially algebra, on the models. And that requires a fairly limited vocabulary. You need to have a representation of your system that it can reason about and transform. And having just a Turing-complete imperative system for doing things you can't really reason about it. So we need a limited vocabulary from the start in order to do the transforms that ModelingToolkit does. And in the case of the macros, you see this declarative system used to describe things, which works very well because it has a limited vocabulary. It doesn't open you up to being able to run just arbitrary Julia code in creating those systems. And these macros then provide this declarative feel in describing the behavior of components and systems. And they ultimately leverage the Julia language, which is this imperative environment. And so there's this sort of tension there, as I said, between the sort of imperative side and the declarative side. And when is it, when do you have to stay within the declarative aspects, and when can you use the imperative stuff? Yeah, and then there's a whole bunch of sort of implied semantics around those Julia macros that are not necessarily obvious if you were to just boot up VS Code in Julia mode. It doesn't know what those macros actually mean, and so it can't really enhance the functionality there above and beyond what is just Julia. So the question is, how do we reconcile these sort of imperative and declarative aspects? So another complication that comes into this is this notion of doing graphical model composition. So everything I showed you before was textual. So when we're using Julia macros, we're sort of inherently using this textual way of composing models. But what if we also want to, at the same time, compose models graphically? And by that I mean, dragging and dropping components down onto a canvas and connecting them up. And so, this is the example of the JuliaSim macro. But we also want to be able to essentially represent models in a form like this, right, which is graphical. And so this is another complication. How do we reconcile these two worlds, this textual and graphical world? Another thing that we are sort of concerned with is round tripping, and I'll explain a little bit more about what I mean by that in a second. But basically, imagine you create a model in a GUI, and then you want to, by dragging and dropping something, and then you want to then edit it as text and then go back to the GUI, for example. So if you built such a GUI, you could write Julia code. You could imagine a system that would take a diagram like the one on the right and could generate the code that you see on the right here. But then what happens when you want to actually edit it in the textual mode and then load it back into the graphical user interface, right? There's this sort of back and forth, what we call round tripping. How would you manage that? If you just have a system that takes a graphical representation and generates code, then how can we iterate on that? Because the graphical information that we need isn't really present in what you see here in this code. Things like where components are laid out, how the connections in the system are routed, and so on. So we get this complication of again mixing this imperative and declarative stuff and reading and writing these things. The fourth complication that comes up is the fact that if you're going to be creating a GUI, today you're largely going to be doing that in a browser or perhaps in Electron or in VS Code. But in a lot of these cases, you're leveraging essentially a web browser, one way or another. And so if you're this applies when you're creating a VS Code extension, is that you're essentially using a web browser as your environment. So in these environments, the GUI itself is generally going to be JavaScript. I mean, you can use WASM, but I'm just sort of setting that aside for the moment. These are essentially JavaScript execution environments. And I put JavaScript/TypeScript here because a lot of the development is now actually done in TypeScript, which is a superset of JavaScript. But evaluating that MTK code, evaluating those macros, just to even figure out what constitutes your system model involves a Julia execution environment. How are we going to do that if the environment where we're developing the graphical capabilities is not a Julia environment? And so the problem that we have in this case is that we have ModelingToolkit and this amazing ecosystem in Julia as sort of our starting point. And at some point we have to deal with this fact that we have the browser, VS Code, and potentially other environments that we'd have to deal with, but these are the big ones. And so we have this sort of middle layer, what I refer to as the sort of composition layer, how we actually build models. We're not actually running code, we're just talking about the construction of the models themselves, what they're composed of. And how do we do this, right? Are we going to do this in the sort of browser? Are we going to do this in Julia? And if so, how do we get these two, the top layer and the bottom layer, to really talk to each other? Do we build some HTTP API? What do we do there? So those are some of the complications that we were looking at. And so the question is, how do we address these? So in terms of model composition, it's not a question of whether we do this in Julia or in TypeScript. I think that's sort of the wrong question. Because those are still both imperative languages. We're really not dealing with this tension between the declarative aspect and the imperative part in these cases. So what I felt, in my opinion, we really needed to do was to come up with a declarative vocabulary for what we mean by describing models, and just focus on that. And so if we do that, then we have a system that we can sort of reason about these models, these compositional systems. It's not a Turing machine, right? This is just essentially a formal representation of what we mean by a model, what it means to connect something, how we define the parameters and physical types of things. That's our vocabulary. And so the solution that I came up with here is this JuliaSim Modeling Language, for better or for worse. So in the JuliaSim Modeling Language, we have this declarative domain-specific language, right? So it's neither TypeScript nor Julia. It's just a very limited language for describing the composition of models and the rules about composing models. So you can describe the model behavior, the fundamental equations that are in these models, but you can also describe the composition. So if you want to build a circuit model, the idea that you bring in a resistor, you bring in a capacitor, you connect those up. So that's not a equation or math-based sort of composition. That's just relationships between entities. from my perspective, the nice thing about it is that it runs natively in a browser. The actual language kernel that implements all the semantics and the parsing is all done in TypeScript. It allows for a bunch of strong static checks to be done on these models that you're composing. Because it's running in the browser and it's integrated into the graphical user interface that's developed, you can get immediate feedback on things. If you try and connect two things that shouldn't be connected, you get immediate feedback on that. It doesn't have to make some HTTP request and then come back with an error to tell you, oh, that wasn't allowed. It can make those decisions immediately, and in fact, generally synchronously in the browser, so it's really immediate. And this being integrated into the browser allows us to create this fast reactive user interface. So the thing is, though, that there's no imperative semantics involved here. So there's no functions. All that stuff comes from Julia. So the scope of what I'm talking about here is very limited. It's just about describing the composition of the models. Anything that involves actually running anything imperative, loops and ifs, well, not quite ifs, but non-ternary operator kinds of if things. That's all done in Julia. So JSML, the closest analogy I can describe here is that JSML is like HTML or XML or something. It's just trying to capture the representation of a very specific domain. So here are some examples. So you have the MTK macros on the left. You have the JSML code on the right. So one of the things I'll point out is that we have the notion of physical types in JSML. So there's a volume type, and it includes the units of volumes. So actually, this should be voltage. I just realized that's a typo. It should be voltage. My apologies. But and then you can do things like you can define a connector, which has a voltage and a current. You can do the same sorts of things that you do in ModelingToolkit's macros, which is to extend from an existing base class and then add additional equations. And similarly, when you compose systems, you do it in a similar way. You can see sort of side by side, describing the same system in both. So you might think, okay, well, this is just an alternative syntax. What's the benefit of this really over the MTK macros? Well, the one is that we can do it in a browser, and that so we don't have to have a Julia environment running. Another is that we can add graphical information to this, and so I'll show some examples of where this comes in. Actually, I skipped one slide. One slide I wanted to point out is that when we generate Julia code, we actually generate the MTK code from these JSML component models. So ultimately, it all ends up being in Julia. This is an important point. But we can also walk through the definition of that component, like this resistor, and extract out a bunch of useful information, and then automatically generate the doc strings for the functions. And this that shows up when you just do a help in the Julia REPL on that component. You get to see all this information. What is R? What's its default value? What are its units? What connectors does this have? What internal variables does this component have? Which is relevant for, like, Ayush gave a talk before me about the symbolic indexing. And that's actually referring to these sorts of things, the VNI values that are inside of those. So that's one thing we do, is we generate the doc strings. But we also have this concept of metadata that we bind to these definitions. And normally, if you're looking at this in a graphical user interface, you won't even see this metadata. This is the textual representation. But when you're doing graphical composition, we don't see this. And when you're editing these things in VS Code, they can be folded up, so you don't see them. So I just want to make it clear that this might seem noisy, but the point is it's not in your face all the time. But I just want to point out that it exists. So this is an example with a connector pin here that we can define the appearance of one of these connectors on a resistor or a capacitor. And so we use metadata to do that. So within this connector definition, we have this metadata, and we have a schema that defines what's legal metadata, exactly what form it should take, and we can validate that the metadata is legal and everything. So this allows us to define the icons that will be used. It allows us to define some of the attributes that are used when we stroke connections, for example, so that we can say that when we stroke the connections, that they should be a certain color. And so anyway, so that's the metadata field in the components. Another aspect of metadata is if we were building, for example, a circuit model, and you can see that over here. There's a couple of different things we can do. One is we can specify the placement of these things. So the metadata attached to this allows us to say that this particular component, this resistor, should appear here in the diagram. It should be rotated in this way, the exact extent of it, so we can make it larger, smaller, things like that. That's all in there. And then we can also include metadata that includes the routing between the connectors. So there's a connect statement back here that connects these three things. But what the metadata is doing is it's allowing us to specify how that's routed, including things like junctions within the routing. So I won't go into exactly what this metadata means, but it allows us to handle these sorts of complex routing descriptions. And with this information, we can then just render the graphics for this component. We can generate a graphical representation. Another thing that we can do, though, with metadata, in addition to just graphical stuff, is that we can include other information. So, for example, we have this sort of reserved this JuliaSim namespace in metadata for stuff that is specific to our tool, but you can create other namespaces. So, for example, Gary at Boeing wants to put metadata into his component. He can add that metadata under a separate namespace called Boeing, and then he has free reign over that stuff. So he can put part numbers in there. He can put processes or gateways or whatever information he wants to put in there. He can put in there, and it's preserved. In this case, this is another example of generating a test case, right? So we've specified some metadata in here that describes a particular test case called case 1, the stop time for it, expected outcomes, expected values for that test case. And what this actually does right now with the JSML compiler is it generates essentially the runtest.jl file, runs the simulations, so that, and then compares the results at that time. So what that means is that you can just go in and run test on your package, and this declarative chunk of metadata gets turned into an actual imperative test case that gets generated. Okay, and so the result is that you get stuff like this. This is an actual screenshot of JuliaSim GUI, and I see some of the developers of the JuliaSim GUI in the audience. Anyway, the net result of all of that metadata is that we can then render these sorts of things. We can generate the information that you see on the sidebar, right, about what components are defined within a given package. So this is JuliaSim. So it reads and writes JSML. It allows you to do drag and drop model composition. Each component library is just a normal Julia package. The way that this works is that the JSML representation is used to generate Julia code, and that's then just a Julia package, which you can package up, put into a registry. You can add it as a dependency, import it into your system. So it leverages the Julia package manager to manage all the dependencies, and it uses JSML metadata to handle the layout and the routes and things like that. You can see, for example, a junction is rendered here. Then we have JuliaSim Studio, which is an extension for VS Code, which is another way to interact with this. Because the language kernel is written in TypeScript, it not only runs in the browser, in the previous example I showed you in JuliaSim, but it runs very nicely in VS Code. So I have a quick, I'll show a video in a minute, but this adds syntax highlighting. It integrates in the JSML compiler for doing the static analysis and the code generation right in VS Code. Each component library is just, as I said, a normal Julia package. So it works with the Julia extension, with the Julia Hub extension, you can do things like metadata folding, which I alluded to earlier. And then it also still supports being able to render a model. So you can still look at the graphical representation even when you're in VS Code. So here's just a quick video that's going to walk through this. And I'll try and make this full screen. If I can figure out how there used to be a button to do this, and now I don't see it. Shoot. Okay, well, anyway, I would just be a little bigger in that case. But you see that the metadata is folded there. I open up a Julia REPL. I can see that there's a problem with the types here. I get the immediate feedback. There's a problem there. I can go through and show you the resistor model and the 2-pin model, just looking at the code and how it's syntax highlighted. If I bring up the Julia REPL, I can show that if I type the name of a model, it actually renders the model for you right there in the VS Code, and I can perform this test that you see here. So it'll go off. It'll run the tests that I defined that I talked about before, which are going to compare. They're going to basically check for regressions. They're going to make sure that the models there's a sort of test specification for those models. and it's going to check to make sure that the initial conditions are what we expect and that the final conditions are what we expect. And in the future, I want to add the ability to actually look at the trajectories themselves and actually make sure that the trajectories are within some tolerance of an expected result. So anyway, this will run through and it'll say, oh, you passed all your tests here. I don't know. I guess I won't bother waiting for that. And so in terms of future work, there's a lot more static checks that we could be doing. I showed one example really quickly in that VS Code thing, but it went by very fast, where if you were to define, if you were to try and use a component that didn't exist, if you tried to use resistor 2 as your resistor and there is no resistor 2 anywhere in the set of dependencies that it has, then it'll immediately flag that as an error, right? And this is the difference between the MTK macros and something like this, because in MTK, it would find that error, but only at runtime, actually, when you try to instantiate the system, whereas we can get immediate feedback in the VS Code extension that no such thing exists. There's a lot of these kinds of static checks that we can do, and I think ultimately, for an engineer, I mean, my background is in engineering. For an engineer trying to work with these systems, I think the more that we can front load a lot of these things, the better it'll be in terms of their experience, giving them very specific feedback on what's wrong with their systems. Also, we're working on expanding the set of standard library components that are available. So we're working on an electrical component library, mechanical component library, hydraulic, thermal, and then control systems. And then ultimately, we've been doing a lot of interesting work with state machines. We want to be able to integrate that into the language as well. So, yeah, there's a lot of cool stuff I think that we can do. This is really, I mean, this is the first public talk even on JSML. I mean, it's really, very fresh. And I think there's a lot we can do there. So a couple of conclusions. I mean, we have this declarative representation for model behavior and model composition. We can translate this directly into Julia code using MTK. The language semantics can be run natively in the browser for immediate feedback. And of course, elsewhere, we have a command line compiler. We have the VS Code extension. It's a single representation that allows us to support quite nicely both the text and the graphics and to actually go back and forth between them. So, there's no compromise here in the sense that if you want to be doing stuff in Git or want to be doing things in CI in a sort of headless mode, you can do that. Or if you want to be using a graphical user interface to compose models, you can do that. We don't have to make this sort of false choice between having a nice GUI desktop tool and having something that can be automated in CI. We get both of these. It's readable and writable by both humans and machines. And it has this limited vocabulary by design that constrains the expressiveness so that we can actually reason about things, and delegates, as I said before, all the imperative stuff over to Julia. So it's still very much leveraging Julia and built on top of Julia. All the functional pieces come from there. And that's my talk.
Okay. Well, there's a sea of questions. So I don't know. Yeah, somewhere there. Let's go. Yeah.
I have not tried it with Pluto.
Yeah, okay.
That would be a question for
yeah.
Penny.
Please speak to the microphone. So yeah.
Will this also work with Pluto?
I can answer that. The answer is no right now, but since this works totally in the browser, it's something that we can integrate.
Yeah, I'm afraid. Yeah, you need to speak to the microphone. Otherwise, it will
okay.
not be,
I'll speak for Penyatis. So I guess. So yeah. So he's actually one of the developers of the JuliaSim GUI, and he's also one of the contributors to Pluto. So he says eventually, yes, we're in good shape there, but not yet. I think I captured his sentiments there. Okay.
Thank you very much for your nice talk. One question. Are there plans to implement arrays of elements?
I have some ideas on how to implement arrays, and there's already array support in MTK. It's just a question of time. I mean, there's a lot of fronts on which to try and expand the capabilities. That's definitely one of them. It's a challenge when you try and do arrays and combine it with the graphical user interface. And so we have to really give some thought as to exactly how we want to express that both graphically. Textually, it's pretty straightforward, I think, but graphically, it's a bit of a challenge.
Thank you.
Yeah, perhaps somewhere there.
Somebody pick somebody.
Yeah, thank you. So this reminds a little on the Modelica annotation system. So I'm pretty sure that there are some improvements compared to Modelica, but are there any? Did you try to make some things better compared to the quite old Modelica?
Yeah, so in fact, I will say that at the American Modelica conference, I've submitted a paper which will hopefully be accepted that addresses exactly that point, which is to say that Modelica is a very widely used technology, but I was around when it was developed. It was developed 30 years ago, and so there are a lot of things that changed in the technological landscape, which is no fault of Modelica. I mean, time passes, things change, technologies change, and so yes, I think there are opportunities that JSML can take advantage of. And what I tried to do in this case was, being pretty knowledgeable about Modelica as well, was to try and take what really worked well in Modelica and incorporate that. So you spotted that with the annotations. Although those are JSON annotations, I should point out this is an example, right? JSON is now ubiquitous. Everybody can read and write JSON. Modelica has its own structured data syntax. There's just no reason to have that now. So we just switched to JSON. We use SVG for graphics because there's no reason to use something other than that. So those are examples of how we tried to modernize some of those concepts.
Yeah, thank you very much.
Yeah, we'll have just one more question there, and for the rest, just catch Michael after the presentation. Sorry.
Yeah.
Hi, thank you for the presentation. Do you also have support for discrete events?
Well, I mentioned the state machine stuff in there, so that's one aspect, and that's another example where I think we can actually move beyond the capabilities that are in Modelica. We have a vision for actually having primitives in the language for state machines specifically, as opposed to component libraries that do state machines but are a little awkward to use. So yeah, we have a plan for actually integrated capabilities for state machines. So when you describe the behavior of, for example, a clutch, and the sticking and slipping modes of a clutch, that you could actually represent that as a state machine instead of a bunch of discrete variables that you kind of knit together with when clauses into a state machine. You could actually represent directly in a state machine. So again, that's one of the many fronts, along with array components, that we want to get to, and we have, I think, pretty specific ideas about it. It's just a question of bandwidth and demands. But yeah, I certainly hope so.
Okay, let's give it up for Michael again. Yeah, great.